Okay, this is a review problems for the test number 3 in Math 220. The topics are pretty much eigenvalues, eigenvectors, and eigenspaces, and the trajectories of given matrices. So you can take a look at that first problem. It says, describe the trajectories corresponding to the matrix A. That's 0.3, 0.5, negative 0.5, and 0.3. So let's start on that. First, you may notice this is of the form A, B, the opposite of B, A. And these have complex eigenvalues and eigenvectors. Those eigenvalues are supposed to be of the form lambda is equal to A plus or minus BI. You can show that pretty quickly in this one by saying if you take 0.3 minus lambda and 0.5 and then negative 0.5 and 0.3 minus lambda, you set that determinant equal to 0, you'll get 0.3 minus lambda times 0.3 minus lambda, so that's 0.3 minus lambda squared, and then minus the product of negative 0.5 and 0.5, which is positive, will be a negative 0.25, so it'll be plus 0.25 or 0.5 squared, if you will. And then we subtract 0.25 from both sides. 0.3 minus lambda squared is equal to negative 0.25. Now we have to take the square root of both sides. So you take the square root, and the square root of 0.25 is 0.5, of course, and since it's negative, it's 0.5i. We get the absolute value of 0.3 minus lambda is equal to 0.5i. So 0.3 minus lambda should equal positive or negative 0.5i. And adding lambda to both sides, and then subtracting and adding 0.5i from both sides, we get 0.3 minus or plus or minus 0.5i. And so those are our eigenvalues. Now, based on those eigenvalues, we can describe the trajectories, because the trajectories, if you recall, when you have complex eigenvalues like this, and they're the same conjugates of one another, then the magnitude of lambda tells you how those vectors will change as we apply this matrix multiplication to them. So we get lambda, the magnitude of lambda is equal to the square root of a squared plus b squared, and a is 0.3 and b is 0.5, and so that's going to give us the square root of, that's 0.09 plus 0.25, which is 0.34. The square root of that's about 0.6, I think. If we do that on the calculator, I think we'll get 0.58 something. So I'll say approximately 0.58. So that is, we usually call that r. The magnitude of lambda we call r. That's the distance of this, the magnitude of those vectors. So that means that every vector in this trajectory will be 58% or 0.58 times the magnitude of the previous vector. If you remember, this ends up being either a contraction or an expansion of r0, 0r, and then it's a rotation. Well, first it's a rotation, that doesn't really matter here. Cosine phi, and either plus or minus sine phi here. In our case, we have a minus sine phi, and so this minus in this corner means it's going to be a clockwise rotation. Remember, if it's up here, it's a counterclockwise in the positive direction. So this is cosine phi. That's the standard matrix of rotation for a clockwise rotation. And so we know that that the cosine of phi, from this we also know that the cosine of phi, which we use to find the magnitude of the rotation, is equal to a, that coefficient, over r. So in this case, it's going to be a, in this case, is 0.3, and r is the square root of 0.34. So that means phi is going to equal the inverse cosine of 0.3 over the square root of 0.34. Put that in your calculator in degree mode. That turns out to be about 59 degrees. So that gives us a pretty simple way of describing that rotation then. The vector, any vector in that trajectory will be contracted. It'll be shortened, be about 58% of what it was previously, and it'll undergo a clockwise rotation of 59 degrees. So that means a vector would undergo a 59-degree clockwise rotation, and a magnitude change with a factor or by a factor of r in this case, which is about 0.58. Okay, so that is the conclusion of that. By the way, that would be, sorry, since that's that, we would say that is spiraling towards, or toward, the origin. Spiraling inward toward the origin. So these vectors, if we just did a rough sketch, if you took a vector out here and applied this to it, it would be a little more than half its length, and that would take about a 60-degree rotation, or you could rotate it 60 and then shrink it. And that's like at about a 45. So here's a vector, then it goes down to here, it's about half as long. Then, it would go down to about another 60 degrees, be right about here, it would be even smaller, that length would be cut in half, then another 60 degrees it'd be cut in half, then another 60 degrees, so it would spiral in to right here. It would look kind of like this if you follow the tips of those vectors, and it would get closer and closer to the origin. It would never really equal zero. It's always going to be about 58% of the previous, but it'll spiral in pretty quick. Okay. Problem number 2 is to find the eigenvalues, eigenvectors, and then a basis for the eigenspaces and the actual eigenspaces for the matrix A. And then plot the trajectory of the vector 3, 4 under that transformation. So here's the matrix 3, 1, 0, 5. So how do we find the eigenvalues? Well, this is a triangular matrix, so the eigenvalues are just the main diagonal elements 3 and 5. So we'll have for the eigenvalue 3, the eigenspace would be determined by setting a minus lambda I times x, all the eigenspace would be all the vectors x that would make that equal to 0. Remember, an eigenspace is a null space, really. Special null space. And so let's go ahead and do that. We'll subtract 3 from the main diagonals, right? That's what that means. So we'll get 3 minus 3 is 0, and we get 1 there, and then 0 and 5 minus 3 would be 2. So we basically get this. The eigenspace is the solutions of this homogeneous equation. And so here we see that x sub 1 is free. and x sub 2 is a basic variable. This is 1x sub 2 is 0 and 2x sub 2 is 0, so we know that x sub 2 from this is just equal to 0, as simple as that. So the basis for the eigenspectors is going to be, eigenspace is going to be 1 for the free variable and 0 for that, and the whole eigenspace is going to be x sub 1 times 1, 0. So all possible vectors that would solve this. So here's the basis vector, and this is the eigenspace, all corresponding to lambda equaling 3. Now for lambda equal to 5, we get 3 minus 5 on that angle, and 5 minus 5, so that should be negative 2, 1, and 0, 0. Now, of course, this is a homogeneous system that we're looking for a solution for, and so we can clearly see here that x sub 1 is a fixed variable and x sub 2 is our free variable. So this tells us that negative 2x sub 1 plus 1x sub 2 is equal to 0. So negative 2x sub 1 is equal to negative 1x sub 2. So x sub 1 is equal to 1/2 x sub 2. So that gives us a basis vector of x sub 1 is half of x sub 2. That's a half there. And 1 for x sub 2 because it's the free variable. And the whole space would be, this again is our basis vector. And this eigenspace is x sub 2 times 1/2, 1. Now, by the way, the basis could be any multiple of this would be a basis vector, since it's just one vector, and any multiple of this would be the basis, would be a basis for this eigenspace as well. So we could have said this is 1, 2 for that matter, and this would be x sub 2 times 1, 2 if you'd like. But this is all for lambda equaling 5. And now it says plot the trajectory. So this is our basis, this is our eigenspace, and there's our eigenvalue for those corresponding eigenvalues. So if we plotted that, I guess I'll get a piece of graph paper for that. A piece of graph paper. The reason I want to do that is I have to plot the trajectory a little more closely. It says to plot the trajectory of this the vector 3, 4, which is clearly not an eigenvector. Okay, so let's zoom back out there. So it's not an eigenvector, so it won't be on the eigenspace, but the eigenspaces will influence it. So if we plot those eigenspaces for lambda equal 3, we get 1, 0. Well, that's just along that horizontal axis. So let's get a straight edge for that. So just make a horizontal axis there. Since these are all positives, I think we're going to start this kind of low. And that's the eigenspace for lambda equaling 3, because that was 1, 0. So that would be 1, 0 would be that vector, and it's all multiples of it. And then the eigenspace for lambda equal 5 is all multiples of 1, 2. So if we go over 1 and up 2, we get that point. We can go over 1 and up 2. All these would be eigenvectors on the eigenspace, and of course all multiples are those values in between. So this is the eigenspace for lambda equal 5, and that is a repeller that's heading away from the origin. This is also a repeller heading away from the origin. I didn't draw that in class today, and I should have, because I was treating this as an attractor coming towards the origin when I talked about that in class. So, and that was an error. The vector is 3, 4. So the vector 3, 4, 1, 2, 3, 1, 2, 3, 4 is close to that eigenspace, but this is a repeller also. So 3, this This eigenspace does have a pretty good influence on this. It's not just influenced by that eigenspace. So if we do a trajectory, we would take this matrix 3, 1, 0, 5 and multiply it by the vector 3, 4. If we do that calculation, we get 9 and 4, which is 13, and we get 0 and 20, which of course is 20. And so that's the first point of trajectory. So 13, 20 would be over, there's 1, 2, 3, 4, 5, 7, 8, 9, 10, 11, 12, 13. And then 20, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. That's going to be way up here. So let me do that again. Okay, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Now, look at that, goes from here to here. If this was an attractor, this would be drawing in. And when I drew it, sketched it quickly this morning, I thought, oh, well, that's going to be going into that because that was an eigenvalue of 3, which also draws it to the right. So this trajectory actually won't go into that eigenspace like the ones we did yesterday in class because this is a repeller. They're both repellers. If we did this trajectory again, we would take 3, 1, 0, 5 and multiply that by 13, 20. And that would give us 39 and 1 is 59. And then 0, that would be 0 and 100. So 59 and 100, which is off our chart. But if we did a vector in the direction of 59, 100, it would be about 30 and 50, or 15 and 25. That's just a little further this way. 15 and 25 would be 1, 2, 3, 4, 5. It would be in this direction way, 4 times the distance, quite a ways out. So anyway, that trajectory doesn't go actually towards that directly. So anyway, that's just one path. I mean, you could go like this. Say, okay, it goes along there. That's the trajectory at first of that particular vector for at least one iteration. I'm going to continue the next 2 problems on another video.